Quantum tunneling. This is a popular animation that is normally animated with a particle running into a very specific kind of barrier, also known as the step potential. This is one of the fascinating feats of the quantum world as compared to the classical world, and we can discuss more of them in this particular question. So this question in particular wants us to consider the step potential, which is defined as a piecewise function where we're 0 to the left, which we know the solutions for that, and we're at some static amplitude v0 to the right. Notice that this form puts us to where we could set it up in terms of the step function theta of x, which we saw back in question 2.23. I wonder how this step function and the step potential became best friends. But I'd like to point out that this isn't exactly new. This is just half of the finite square well. And we saw this before when we were studying the square well because we were able to split the symmetric well in half, analyze one side of it, and impose the answers to the other side via the symmetry conditions that we discussed when dealing with symmetric or even potentials. So in this question, what we want to do is take a little deeper dive into this particular case and see how it compares to other classical results, which they have a great paper on, and I'll link that below. Anyways, what is this question asking? A, we want to calculate the reflection coefficient for E less than V0. Remember our bound versus scattering state conditions. And we want to comment on the answer. B, calculate the reflection coefficient for E greater than V0. Okay, so reflection, reflection. Now we got to move on to transmission. Show that T is equal to the energy square root of E minus V0 over E, the magnitude of F squared over the magnitude A squared for E greater than V0. What about E less than V0? Okay, so we got both cases of transmission there. Now, what about in part D? For E greater than V0, calculate the transmission coefficient for the step potential and check that T plus R equals 1. That is a great check to have, and we'll see it implemented here shortly. Okay, so in part A, let's try to get our footing with what's going on in the situation. If E is less than V0, then we know that we are in a bounded state and we should be have a certain characteristics of solution from the Schrodinger equation. As such, the complex nature when we do a substitution on the Schrodinger equation leads us to the answers below in the piecewise form. Here, for something to the left, where the potential is 0, we get the natural a e to the ikx plus b e to the negative ikx. Notice that the complex argument here just translates to a bunch of sines and cosines, and that just means we wiggle and we don't blow up anywhere, which is the problem that we're going to have when we're to the right. If we had kept the exponential with a positive sign, then the exponential would blow up as we got to really big X because it's all real, and that wouldn't work. It's important to take a note real quick that we have two different constants here in the exponentials, k and kappa. K is for the traveling because we have an I there as well, and kappa is for the moving to the right past the barrier where we're real, not imaginary. It's sometimes helpful just to have these written out, so we'll just keep them here. And again, notice that these are just substitutions made from the Schrodinger equation. Good to go there. Note kappa, that V0 is less than, or V0 is greater than E, so this is real and positive. So we're good. Kappa is a real value. And now we can move on. Moving forward though, what do we need out of these solutions? Well, for the reflection coefficient, we need the information about the wave on the side of the incident. And in this case, the wave is incident from the left, i.e. we're traveling from the left and approaching the barrier to the right. And thus we need the coefficients A and B, more specifically their ratio. And we can get A and B from the solution set here by imposing the boundary conditions seen in blue and green. Our first boundary condition is the continuity of psi at the boundary wall, which is at x equals 0. So if we plug in 0 here, color-coded in red, all our exponentials go to 1, and we're left with a pretty simple equation. We like that. What about the continuity of the derivative, which is in green? Again, take the derivative, then apply the point of interest, which is at x equals 0. So chain rule gives us IK on the left-hand side and a negative kappa on the right-hand side. Again, now we just have to tidy this up, and we will see that in the next page. All right, so now that we have the boundary condition 2 implemented, let's go ahead and simplify algebra away. And as we see here, we just solve it for f, which we just divided the negative kappa over. Keep the IKs on the A and B respectively, because it'll make the algebra soon to come a little bit easier. But notice here that in the case of reflection, we do not need the f term, so we want to set these two equations equal to one another and solve away. Ideally, we want to solve for the ratio here, so let's be careful that when we're solving and algebraically, manipulating these things, we get a's to one side, b's to one side, factor them out accordingly. I want to take a note explicitly on how we set these up, where we have a something plus an imaginary term, something plus an imaginary term. And the reason why we do this is because we know we're going to have to take the complex, or rather the magnitude squared. And so what we know here is that for any variable that is a complex variable, the magnitude squared is just the star, the complex conjugate, times the thing itself. And that always leads to the a and b squared terms. So setting it up in this case here just is a little, hindsight being advantageous for taking a ratio. And then, of course, for reflection, we need the magnitude squared. So here you see that we have that a minus ib and the a plus ib. Regardless, it doesn't matter. We end up with a a squared plus b squared term here. So we're good there. Not too bad, not too bad. But what about this and the fact that they cancel out perfectly to 1 does it actually mean? Okay, well, since we have the same numerator denominator, cool, no big deal mathematically. But physically, this is no surprise either. And this is due to the fact that E was less than V naught, meaning that we have a bound state. So if our energy is less than the energy it takes to get over the potential, of course we're going to reflect all the way back. And although there might be some, transient penetration into the barrier, eventually it all becomes reflected. So pretty cool to see our instincts verified, and now we can move on to the next part. So what then are we supposed to do about the case where E is greater than the potential energy? And that's what we're tackling here at B. The only difference that we have to do here in this case of B is now we have scattering states, and those have a slightly different solution. And that's because of what happens with the termination of the fact that these waveforms will die out pretty quickly in the barrier. So let's take a note that the solution set looks like this. Again, A equal IKX plus B equal negative IKX. That doesn't change because we're to the left and the potential is 0. The only thing that changes is what's to the right. And here we have F equal ILX, which last time we just had a real solution. This time the argument is complex. And what we say here is that goes back to the energy conditions. And let's define again what the K and L are, so we can just keep our wits about us. Instead of having V naught minus E, we have E minus V naught now. So that's going to play into effect. So moving forward, though, we still need to rinse and repeat, just like we did on the other term. And we set the boundary conditions equal to. You see the same thing here, does not change. Continuity is what it is. Love the exponentials. And although this is complex, our derivative term, the i's cancel, no big deal. So set them equal to one another again. For reflection, we don't need f. So do the same thing, algebra way, solve in terms of a and b, take their ratio, and then we see that the magnitude squared leads us here. A little bit of, again, some more algebra tricks here. If we can factor out the 1 over L terms here with the negative sign, then we see that we have negative 1 over L. Both of them have the square on it because we're pulling it outside of the square here. But both terms have it, so they cancel. That's just a nice way of writing K minus L and then K plus L. I don't know why that's a 1. It's supposed to be an L. But here we're going to use another clever algebra trick to help simplify this. Pay attention to the fact that L and K here are defined with square roots, and those become abundantly annoying when figuring out solutions. So the idea here is that with the algebra trick we're going to impose, we can get rid of those and simplify down pretty nicely. Alrighty, so like I stated for last time, if going back to the fact that K and L were both defined in terms of E and V, we need to plug these, we need to simplify this thing down and get the K and E's into the solution, which is what we were asked to do. That being said, the trick here that I was mentioning is multiplying by 1 in the form of K minus L squared and K minus L squared. Why do we want to do this? Well, if that's the case, the denominator here will become in brackets K plus L and then times K minus L, the whole bracket squared. And the reason why we want to do this is because we set up this algebraic form known as the difference of squares, and that is a beautiful, beautiful thing because of the fact that we have a square for K, a square root in K, and a square root in L. We just want to get rid of the square roots in the denominator, so here's how we do that. Pretty clever. So K minus L, both of them have a root 2m and h bar term in, so factor it out. Then you're left with E and E minus V naught. Cool. Here, the difference of squares that coming in, you see how we're getting rid of that nastiness here, and we square this entity, square that entity, and we just get rid of all the square roots. Wonderful, wonderful, wonderful. E minus E gets rid of the E terms altogether, and then we're left with a minus sign and a minus sign, gives us a positive V, and this is what we reduce down to. Holy moly, what a wonderful thing. That being said, we still have to plug the blue and green in, and the top part has a 4 on it now, so be aware of that. The bottom part is something squared, and because we have a 4 here with this blue root 2m over h bar, here the green has 2 times 2, which is the same factor of 4, so those cancel. Even better. All our constants go bye-bye, and we get a pure energy equation of square root of E minus the square root of E minus V naught over V naught squared. That simplified down really nice, and this trick of K and L are going to be used later on in the book too, and in several other texts. So please be aware, algebra is your friend. You're either going to love it or hate it. Best that you use it for your advantage though. Alright, so enough with the reflections, okay? We've seen enough of that. I think we're all pretty comfortable with that. The real thing of interest here is the transmission. And of course, we could solve this in many ways. One of the ways that the author suggests is written out in the question that I was too lazy to copy over. But what we can do is have a diagram, and the diagram they provided us was, the incident velocity times some increment dt, and then of course here we have the magnitude there with the direction. We have the transmitted velocity dt and in the direction there. All that to say is that if we're looking at transmission, we have to realize that these are nothing but a relative probabilities, of course. So the probability of transmitting is the magnitude of f times the velocity of vt, and then the magnitude of a squared times the velocity of the incident wave. But of course, in the note that the author gives us in the question statement, the reason why this is okay and why we need to do it this way is because in the barrier, the attenuation, that tells us that we are going to have different speeds, and that different velocities means we have to set up this ratio within the interval of dt. So a pretty cool, interesting perspective to take on this, but nonetheless, here we need to find the ratio of Vt, Vi, and of course, if we go back to what we learned from the in the free particle, we saw what we had to do as far as our conditions on the velocity of a particle. And so here we know that the total energy up top is going to be E, the leftover energy, or rather E minus V naught, which is the leftover energy available since E was greater than V naught. And then here the incident is just going to be E because that's what was given to the system. So this is the difference of energy, so the leftover energy. And here we have the energy of the system. However you wish to do it, we need to simplify this down, so combine the square roots, cancel the 2m's, and we're left with E minus V over E. And again, to me, this makes intrinsic sense because if I'm going to hit the barrier, I'm going to lose out of my total energy the potential that was at the barrier. So that makes sense. Here, of course, we just have F over A. That's our probability of occurring there. So the total statement here, pretty easy, pretty nice. The application of this is kind of messy, so let's see how we do that from a different perspective as well. Okay, so the other perspective of interest here is the probability current perspective. Of course, after we've touched on Griffiths, we know what probability, or not probability, but current density is. Here, of course, Griffiths, being the author of both books, likes using probability current density as J as well. And this, of course, was touched on in, I believe, question 2.18. But basically, it just came to the fact that we had Schrödinger's equation written out with the complex conjugate and a commutator-style relation, and the results of the results of the wave equation to the right, or the transmitted current, probability current, is h bar L, again to the right, so we have the solution of L there, over M times the solution to the right coefficient. And then the incident, which of course used K and A, because that was the incident wave form that we had here. If from this perspective, with the Schrödinger equation, based on the definition of J, we can get these pretty quickly, and it simplifies down because M and H bar again cancel, so we're left with L over K times F squared over A squared yet again. And of course, if we go back to what we saw with L and K, both of them have an energy term in them, this is what we expect naturally. The E comes from the K, and the L had the E minus V naught, so this is the natural extension, or natural simplification, and it's exactly what we expected. And from this, from whatever perspective you use to start these questions with, whether it was the probability with the time domain or the time interval like we had last slide, or this perspective, in either case, if E is less than V naught, the barrier would stop the particle from moving, and so transmission would be zero. Easy enough. We showed case this earlier too in a reflection state when the reflection coefficient was 1. So if reflection's 1, T has to be 0. So we're good there. Everything checks out. We're looking good. Now the interesting part is for E greater than V naught, and what can we do for the transmission coefficient in this case? And so if we pass this along, okay, we know that we're going to need F and A, so we're going to have to find an explicit expression, but we already applied the boundary conditions to the scattering state of E, V naught, and part B, so let's use those equations. There is no right way to solve these, but whatever way is easiest, take that approach, because algebra, again, love it or hate it, it's going to be a part of these things forever. That being said, I multiplied the continuity at A of just a wave function at x equals 0 by K, which I highlighted in red, and we see that by doing so, if I add these equations, I can eliminate B since they have different signs, and that's just let the equations roll. That being said, let's simplify it down then, and you see that we get 2Ka plus 0 because the b's cancel. We don't need the b, so who cares? And then we see that we have K plus L times F. Find the ratio, of course. Divide the K plus L over, divide the 2A, or the 2K, rather. Divide the K plus L over to the 2K term, divide the A over, and we see that we get this fraction. Just as before, we're probably going to use a math trick on the 2K and the K plus L just to simplify the energy expressions. Alrighty. So, like I said, we have to find the coefficient now. Well, transmission coefficient as a total. So we plug in the ratio of F over A here. Remember that we had L over K in the original form. And we want to stay in L and K's as long as possible because they simplify a lot easier than carry all the square roots around. So let's go ahead and see that. Again, K and L here are going to be real, so we're good. Take them through. We get 4K squared, that cancels with a K, as you see there. So in the numerator, I end up with 4KL, and in the denominator, I have K plus L squared. Again, we're going to use that multiply by quote 1 trick, where we have K minus L squared. Again, we saw what happened earlier, difference of squares. And okay, we already found these results earlier. Let's plug them back in. K being the first square root, L being the second square root. Notice here how I have 2m h bar to the 2. Again, I have it squared, so I have 4 copies of root 2m over h bar in the denominator. I have 2 copies from the blue term here. I have 1 copy here from the L and 1 copy here from the K. Boom, get rid of them all. And you see that after we do that, we tidy down pretty quickly to 4 square root of E minus V naught. And then here we have the result of F over A, where we have E square root of E minus square root of E minus V naught squared over V naught squared. Totally cool, pretty easy to deal with. But we still have one question to ask. In the scattering state, where we have the reflection coefficient and the transmission coefficient now, both in terms of L and K, do the sums equal 1? Let's find out. Again, being that the fact that these are all relative probabilities, meaning that since we can't solve explicitly for F and A, we don't have enough terms there. We have to find a ratio. That's what makes them relative probabilities. Nonetheless, they still need to sum up to 1 because they are probabilities acting together. That being said, in the blue term, we have our T, our transmission coefficient for the scattering state of the step potential. We saw that very quickly. We just saw this. And then here, we also saw what we turned into with the algebra tricks. Use them all. This is also an algebra trick, but it's pretty quick and easy. We have a common denominator, put them together. Now we're done with the denominator. Then we see here that we have a square here, so just FOIL it out. That gives us a k minus 2kl plus L squared term. This term here cancels with 2 from this blue term, so we're able to still have a remaining of 2 there, which turns into another factorable form of k plus L. And here, numerator is the same, denominator is the same. We have 1, and that is exactly what it should be. Now, quick note here, this is also representative of conservation of energy too. The energy I put in has to be the energy I get out. So the energy that is reflected and the energy that I transmit has to be the same, or when I add it together, has to be the same as the total energy that I gave it. So this is also a conservation of energy equation, which was highlighted pretty extensively in the E&M book, but great to see it coming back again. And as always, until next time, happy learning.